Find the radius of the curve. In this problem, points A, B, and C are plotted on an xy plane, where the coordinates of all 3 points are provided. If a circular curve is drawn connecting these 3 points, the problem asks to find what is the radius of such a curve. We'll equate the radius to the distance between points A and O. Since point A is at the origin, the equation for the radius simplifies to the root sum squared of the x and y coordinates of point O, which is the point defined at the center of the curve. We'll find the coordinates of point O by finding the intersection of lines DO and EO. We can define line DO by drawing a chord AB and then drawing a line normal to chord AB which passes through the midpoint of chord AB, which occurs at point D. Line EO is generated in a similar fashion. Chord BC is drawn out, and line EO bisects and is perpendicular to chord BC. Using geometry, we can show how the center of the curve, point O, must coincide at the intersection of lines DO and EO. Both triangle ABO and triangle BCO are isosceles, since line segments AO, BO, and CO are all equal to the radius of the curve. Then, from the law of sines, we substitute in the radius for lengths AO, BO, and CO into the denominators, and the sine terms drop out, such that angles ABO equals angle BAO, and angle CBO equals angle BCO. For these two pairs of angles to be equal, point O must lie on the line which bisects and is perpendicular to chords AB and BC. If point O lies not on either line DO or EO, this would violate the angle equalities which we know to be true based on geometry. Therefore, all we have to do is solve for the point which lies on lines DO and EO. The general equation for a line in 2 dimensions is y minus y naught equals m times the quantity x minus x naught. In this equation, x naught and y naught are known coordinates of a point on the line. So for line DO, we'll determine the x and y coordinates of point D, and then substitute those values in for x naught and y naught. For line EO, we'll use the same x and y coordinates, but for line E. The variable m represents the slope of the line in y over x. To the equations for line DO and line EO, we'll add a subscript DO and EO to their slope terms. Next, we'll use the coordinates of points D and E by averaging the given coordinates of points A and B and points B and C, respectively. After plugging in the coordinates, we know that point D is located at x equals 1, y equals 2.5, and point E is located at x equals 3.5, y equals 5.5. After plugging in these coordinates, we still have to solve for the slopes of lines DO and EO. First, we'll find the slopes of lines AB and BC. Then we'll determine the slopes of lines DO and EO, since the slopes of perpendicular lines in 2 dimensions are negative reciprocals of each other. After substituting in the coordinates of points A, B, and C, we find the slopes of lines AB equals 2.5 and the slope of line BC equals 0.333. After taking the negative reciprocal of these values, we find the slopes of lines DO and EO equal negative 0.4 and negative 3. Now we have the equations for lines DO and line EO, which simplify to 0.4 times x plus y equals 2.9 and 3 times x plus y equals 16. Subtracting the first equation from the second, we find x equals 5.04. Substituting 5.04 in for x, we can solve for y, which equals 0.88. 5.04 and 0.88 correspond to the x and y coordinates of point O, the center of the curve. Plugging in these values into our equation for the radius of the curve equals 5.12 feet. When reviewing the possible solutions, the answer is B.